Winter is nature's cold weather test lab, where delicate crystals materialize out of thin air. And freezing conditions spin cars out of control. There's fascinating science behind every phenomena of winter. From the secret of what makes ice slippery, to how your brain reacts to the cold, and the amazing connection between a hibernating squirrel and human organ transplants. We'll separate fact from frozen fantasy. Is it true that no two snowflakes are alike? What packs more punch, a hurricane or a blizzard? And when the mercury drops, what really happens to mosquitoes? It's everything you always wanted to know about winter, but we're too cold to ask. It's the science of winter. The mercury is dropping, icicles are forming, and you're digging out last year's hat and gloves. Winter has arrived, and it's cold.
Oh, it's freezing. I can't feel my feet. My toes are like crunched up. I'm wearing like 3 pairs of socks.
Winter can paint a beautiful picture, or stop you dead in your tracks. But there's a scientific answer for every frozen question about the coldest season. Here are the cold scientific facts, beginning with the start of winter. Winter officially arrives on the shortest day and longest night of the year, known as the winter solstice. It lands between December 21st and 22nd for those living north of the equator. But why does it get so cold? We're all taught it starts with the Earth's orbit.
Something to do with the angle of the Earth and the sun.
In the winter months, we're pretty much out here, further from the sun.
Because of the air masses that move across certain latitudes.
But I think we're just further away from the sun.
The real reason it gets cold isn't the distance, but the angle of the Earth to the sun.
Well, it's colder in the winter precisely because of the low sun angles. It really comes down to how strong the sun is.
Like a spinning top frozen in an off-kilter position, the Earth is tilted on its axis, fixed at 23.5 degrees. As we orbit around the sun, the North Pole is angled furthest away from the sun on the winter solstice. Think of the sun like a flashlight shining on a piece of paper. Directly overhead, the light is concentrated. At an angle, the same amount of light is spread out and less concentrated. It's the same with the sun. The Earth stays colder because the sunlight's warming effect is less intense, much like sunrise and sunset are cooler than noon.
You experience this every day. Morning and dusk are cooler times of the day than noon. High noon, you can feel the sun right over your head beating down on you. But in the morning, when it's low on the horizon, those rays come in at an angle rather than straight overhead. And it's that angle that makes those rays less intense.
The seasons are reversed when you cross the equator. While the northern hemisphere is chilling out, tilted away from the sun, the southern hemisphere is warming up, angled toward the sun. That's why when our Australian friends are donning bikinis, we're putting on hats and mittens and fighting off the cold winter air. That cold air is just one of 3 basic ingredients in the recipe for a winter storm. The other 2 are moisture and lift. An example of lift is a mass of warm air riding up over cold air when the 2 collide. As the warm air rises, it cools, and the water vapor it holds begins to condense, creating a cloud, and sometimes precipitation. The most common storms aren't just snow either. They're more often a dangerous blend of rain, ice, and snow. The different kinds of precipitation following the different temperatures.
On the warm side of the storm, you'll tend to have rain and sometimes even thunderstorms. Right on the boundary, you might get the sleet and the freezing rain. And then on the cold side of the storm, you have all the snow.
A light snow flurry can be picture postcard beautiful. A strong snowstorm can bring traffic to a halt, but a blizzard can cause enormous damage.
The difference is a snowstorm is just a large amount of snow coming in a short period of time, whereas a blizzard implies that there is wind and blowing snow involved with the snowstorm. So it's a little more than just heavy snow, it's blowing snow as well.
By definition, a blizzard packs winds in excess of 35 miles per hour and at least 3 hours of blinding snow, reducing visibility to 1/4 mile or less. It was late in the evening on Friday, March 12, 1993, when one storm began to grip the eastern third of the United States. Forecasters saw well in advance that the storm would be extremely powerful, citing a confluence of factors said to occur about once in 500 years. Cold air blew down from the Arctic in an unusually steep pattern and met warm, moisture-laden air coming up from the Gulf of Mexico. This winter storm was so massive, it took on the name Superstorm. In the course of 3 days, this monster would dwarf even record hurricanes.
Most people don't realize this. Hurricanes generally are much smaller, not in intensity, but smaller in size than a winter storm. We think of something like Hurricane Katrina, one of the great ones and one of the biggest hurricanes we've ever seen, and you compare that with something like the winter storm of March 1993, Hurricane Katrina actually affected a much smaller area than the March 1993 blizzard.
Hurricane Katrina zeroed in on the Gulf Coast states of Louisiana, Mississippi, and Alabama before moving inland and losing energy. The March 1993 superstorm affected about half the country's population in 26 states and lasted 3 days. The superstorm left behind about $3 billion in damage. Snow blanketed the east. Even parts of Tennessee got more than 4.5 feet of snow. At Mount Washington, New Hampshire, record wind gusts hit 144 miles per hour. The South saw record low temperatures, 21 degrees in Mobile, Alabama, -4 degrees in Waynesville, North Carolina. 4 below is cold, but nowhere near the record low in the United States. It occurred on January 23, 1971, along the Alaska Pipeline, about 20 miles north of the Arctic Circle. At Prospect Creek Camp, the thermometer plunged to -80 degrees Fahrenheit. But there's a bonus for putting up with Alaska's recurring cold winters. The state has a fund that has paid full-time residents an average of more than $1,000 a year. But to collect, one of the requirements is staying put through the coldest winters in the nation. The coldest temperature recorded anywhere in the world was during the winter of 1983, near the South Pole at a Russian research facility, Vostok Station. The low, -128.6 degrees Fahrenheit. It takes special equipment to measure temperatures that low. Mercury in a thermometer would freeze solid at -38 degrees Fahrenheit. But a thermometer filled with alcohol can measure temperatures as low as its freezing point, -175 degrees Fahrenheit. We won't find conditions that cold in the lower 48 states. But can it ever be so cold it just can't snow? Not if there's enough moisture in the air. It can be too dry to snow, but too cold to snow is just a myth.
If it's very cold, but there's a supply of moisture coming in, it could still be snowing continuously. It's not really ever too cold to snow.
So provide enough moisture and steady cold air, and the stage is set for a record-breaking snowfall.
The greatest snowfall for a season occurred at Mount Baker, Washington in the 1998 to 1999 winter season. That was 1,140 inches.
That's 95 feet of snow, enough snow to bury a 9-story building. Credit for the record goes to an exceptionally wet and consistently cold winter. 95 feet of snow in one season is more than most of us could handle. But for physics professor Kenneth Liebrecht, it would be the lab of his dreams. Professor Liebrecht studies individual snowflakes by taking microscopic photos of them in the field.
I'm definitely a little obsessed. It's an interesting thing to me, and there's a lot of fun facets to snow crystals, if you'll pardon my pun.
Liebrecht's images magnify the intricate structure of individual snowflakes.
Part of the mysterious thing of snowflakes is, how they form these beautiful shapes all by themselves.
I had always thought maybe it's rain that freezes.
Snow starts in the middle part of the atmosphere, and then when it hits like a certain part, it forms. I don't know.
I guess something about when water freezes, sometimes it just goes, yeah.
Snowflakes aren't made of frozen rain, but rather single crystals of ice that grow inside a cloud. As a matter of fact, snowflake is actually a generic term. It can be an individual snow crystal or a group of snow crystals.
Sometimes a lot of them will glom together into a little puffball, and those are called snowflakes. And both are bits of precipitation that fall during the winter.
But to see how snowflakes are made, you can't just watch them falling from the sky. So in his lab, Professor Liebrecht built a snow machine to grow designer snowflakes. It's called a vapor diffusion chamber. With it, he can recreate conditions in the clouds and witness the birth of individual snowflakes. In nature, the process begins when water vapor condenses onto tiny dust particles in the air. A cloud is nothing more than a huge collection of these minute water droplets. Some will freeze into minuscule particles of ice, the nucleus on which a snowflake can grow.
You start with a little piece of ice, and it grows by water vapor just condensing on the surface of the ice, and that happens in the clouds. And it's during the growth that you get all this elaborate structure.
This snow crystal took 70 minutes to grow. His designer snow crystals are about as big as Lincoln's nose on a penny, but Liebrecht often grows them as small as half the width of a human hair. Most well-formed snowflakes have 6 nearly symmetrical branches.
The reason really has to do with the geometry of the water molecules that make it up and how the water molecules hook together into a crystalline lattice.
The reason snowflakes have 6 sides begins with the basic shape of a water molecule. Each ball represents an oxygen atom. The rods represent hydrogen atoms. There are 2 hydrogens for each oxygen, H2O. When water freezes, the molecules stack together to form a crystalline lattice. They can only fit together, making a hexagonal shape. It is this hexagonal crystal symmetry that ultimately determines the symmetry of snowflakes.
It's really just physics and math, and it's pattern formation, and that's how nature does things.
The patterns emerge as the crystals grow while falling through a cloud. Depending upon weather conditions, crystals can grow into slender needles, thick columns, thin plates, multi-branched stars, or countless other intriguing shapes. So, is it true that no 2 snowflakes are alike?
I think that sounds reasonable.
I think they're all the same. They're all white, they're all small, they're all cold.
Whether or not it's true that no 2 snowflakes are alike, I like to believe that there are no 2 snowflakes that are alike.
There is some cool science to answer this whimsical question.
As the crystal is falling, it changes temperature and humidity because it's going through different regions of the cloud, and each time that changes, the growth changes.
Snowflakes tend to form simpler shapes when the humidity in the cloud is low, while more complex shapes grow with higher humidities.
So the final form you see of a snowflake on the ground really depends on the exact path it took through the clouds. And like people, no 2 snowflakes follow exactly the same path, and therefore no 2 snowflakes look exactly alike.
To perfect microscopic snowflake photography, Professor Liebrecht built what is essentially a high-quality microscope with a digital camera attached. The whole operation is portable and specially adapted to work outside in sub-freezing temperatures.
I like to photograph them by going outside in cold climates, and I built a special purpose photo microscope. Fits in a suitcase, so I travel up to northern Ontario or Alaska and other exotic places in the middle of winter, and I set it up in the back of an SUV and catch snowflakes falling from the sky. Carefully pick them up, put them on microscope slides, put them under the microscope, and get just the lighting just so, and take pictures. It's always fun.
Even the United States Postal Service has taken note by issuing a commemorative set of snowflake stamps featuring his flake photos.
A while ago, the post office called out of the blue and said they wanted to do snowflake stamps using my pictures. So you can buy a set of commemorative snowflake stamps to put on your holiday cards.
Finding picture-perfect snowflakes means finding the place with the perfect conditions.
If you're out photographing, like I do, you want a place where the crystals look nice a lot of the time. And what you need for that is a place where the temperature is just right. About 5 degrees Fahrenheit is perfect for the best crystals. No wind, which the wind will damage them. Humidity should be high but variable. And yeah, there's certainly places that are good for this and not so good. Florida's bad. New York's a little too warm. I find northern Ontario is good, and Michigan and Wisconsin are very good. Vermont is excellent.
While he likes the snow in Vermont and Wisconsin, Liebrecht stamped snowflakes were captured in Alaska, Michigan, and Ontario, Canada. The next time it snows and you feel the urge to catch a snowflake on your tongue, think about this. With every breath, you exhale water vapor, about 2 cups a day.
And that water that you exhale will go up into the clouds, and some of it will be incorporated into snowflakes. And so when you look at a snowflake, on average, there's about 1,000 molecules that came from you. And so keep up the good work.
In February of 1999, the winter-loving residents of Bethel, Maine built a record-setting snowman. Angus was 113 feet 7.5 inches tall. It took 14 days, a crane, and some 200,000 cubic feet of snow to construct. Dozens of volunteers packed snow inside a frame, just like making an icy layer cake. This gigantic snowman outlasted winter itself by not completely melting away until June. Humans are essentially tropical animals. We just aren't born with the right equipment to deal with cold weather.
Very chilly. It's very cold.
A healthy person will feel warm and comfortable until room temperature drops below 77 degrees Fahrenheit. When you feel cold, your body switches on its own self-defense mechanism, shivering.
When your body temperature drops, as it would on a cold day in winter, your body in the hypothalamus sends signals for the muscles to move very rapidly, which we visualize as shivering. This rapid movement of the muscles actually generates heat, thereby increasing our internal body temperature.
Some muscles are better at shivering than others, like the ones in the mouth that make your teeth chatter.
Your teeth chattering in winter is actually a really good example of localized shivering of the muscles around your mouth.
Shivering usually starts in the head and neck, then spreads down through the back and to the muscles in the lower body. Your body can only generate so much heat. Conserving it has everything to do with how you dress.
Layers, lots and lots of layers. You feel like you can't move.
Mom was right to bundle you up, because the fact is, air between layers of clothing provides better insulation than the clothing itself. Layers trap what's called dead air between them. Dead air is not moving and remains heated by the body. Using multiple layers as opposed to one heavy garment traps more of this dead air and thus keeps you warmer. Topping the layers off with a hat and scarf may be half the game, since 50% of your body heat can be lost from your head. That's because its rich, warm blood supply flows through a large exposed surface area. As much as 30% of your body heat escapes through your hands and feet. While a normal body temperature is 98.6 degrees Fahrenheit, the normal temperature of skin is about 91 degrees. As it falls below 50 degrees, surface blood vessels dilate and get wider to feed oxygen and nutrients to the skin. It's the reason your cheeks and nose turn red in the cold. Eventually, as you get colder, the redness goes away. That's because the vessels narrow and constrict as your body tries to keep from losing heat from the extremities. Lose heat faster than your body can produce it, and you face the dangers of hypothermia. Hypothermia begins when a person's core body temperature drops below 95 degrees. Keep getting colder and it affects the brain. Confusion sets in and speech becomes slurred. Drop below 89.9 and the victim may fall into a stupor.
Severe hypothermia occurs when the body temperature drops below 82 degrees. And this extreme cold temperature, the body actually stops shivering and shuts down its metabolic function.
Severe hypothermia will lead to cardiac and respiratory failure, then death.
Engine 1.
In the United States, about 700 people die from hypothermia each year. In the winter of 2002, Olympic gold medal wrestler Rulon Gardner nearly became one of those victims. Rulon was snowmobiling with friends on a mountain in a remote part of western Wyoming.
The snowmobile was beautiful, and it was, really nice. It was a beautiful day. It was a little bit, somewhat cold.
With sunset approaching, the snowmobilers made the first of a series of near-fatal mistakes. They did not stay together. Rulon rode on alone and became lost. Worse, his snowmobile wasn't equipped with a survival kit, emergency food, a shovel, or extra clothing. To find his way off the mountain, Rulon tried following a river.
I actually got, in the river, fell backwards, stood up, and was completely wet, and then that's when I realized I was really in trouble.
With winter temperatures dropping to 25 degrees below zero, Rulon was stranded. The first symptoms of hypothermia were taking hold.
You really don't know when hypothermia sets in. It's not like it's a moment where it's like, oh, there's hypothermia.
Rulon's body began an effort to protect internal organs. Blood vessels constricted, shunting blood away from his extremities, leaving his hands and feet vulnerable to frostbite. Frostbite occurs when ice crystals form within cells, causing them to rupture and die. The first symptom of frostbite is a pins and needles sensation. As the skin freezes, it may throb or ache. Eventually, the area becomes numb.
People say, well, what did you think? What did you feel? Well, it's not a feeling. You know that you're in trouble. You know you're going to be in pain. And the pain actually goes away.
Rulon hunkered down next to a tree in an effort to stay warm. His wet clothing froze. To stay awake, Rulon tried to keep moving, even as he lost the feeling in his legs.
As they went numb, I actually would stand back up, and trying to stand up when your legs are numb is a very, challenging thing. So as I stood up, I'd have to lean against the tree to try to stay awake and hopefully not pass out.
The next morning, after being exposed to 18 hours of extreme temperatures, rescuers spotted Rulon and flew him to a hospital.
My body temperature dropped to 80 degrees as they got me in the helicopter.
Rulon was suffering from severe hypothermia and frostbite. His feet were frozen. Doctors told Rulon to expect the worst: amputation.
The doctor said, there's nothing we can do with those feet. They're frozen solid. You'll never be able to wrestle again because you're going to lose within a week. You're going to lose both feet at the ankle.
Rulon's body temperature dropped 18 degrees, 2 degrees below the point where severe hypothermia should have killed him. Doctors credit his Olympic-class stamina and sheer mass for his survival. The 6'3", 285-pound athlete had more heat-generating muscle and enough insulating fat to protect his body core. After wrapping Rulon in warming blankets, it still took 6 hours to bring his body temperature back to normal. Doctors tried thawing Rulon's feet in a whirlpool tank, keeping the water no hotter than 100 degrees to avoid scalding his frozen toes.
And at that moment, the doctor said, Rulon, there's no blood flow. Your feet are dead.
But Rulon did not give up. In a series of 4 surgeries, doctors grafted live skin onto his damaged toes. Despite the bleak prognosis, doctors saved Rulon's feet. Rulon did lose 1 toe on his right foot. He keeps the amputated toe in his refrigerator as a memento of his harrowing ordeal.
I need a reminder. I need something to remind me for a mistake that I had made, for a decision I had made, and something I had done wrong. And, realize from mistakes I made in the past, not to make the same in the future.
In 2004, Rulon returned to Olympic wrestling and won the bronze medal in Athens, Greece. In the movie A Christmas Story, a youngster takes on a dare and gets stuck with his tongue firmly frozen to a flagpole. In the movie, a hidden suction cup stuck tongue to pole. In reality, the outcome is much more painful.
The flagpole is made of metal and is a great conductor of heat. And so as your tongue hits the pole, heat is transferred from your tongue and saliva to the pole, literally freezing your tongue to the metal.
What should you do if you find yourself in a real-life frozen dilemma?
First of all, don't do it. But if you've already done it, do not rip your tongue off of the pole because you will leave the top layer of your tongue attached to the pole. The best way to loosen your tongue is to put something warm to sort of melt that area that's been frozen. So a warm fluid, warm water would help.
Every winter, travelers wage war against the snow and ice. The science of winter travel is serious business. About 70% of fatal automobile accidents are ice or snow related. Most modern vehicles can get going in winter. It's trying to stop when things get out of control.
Everything you understand about how to operate a car goes away.
And you would just careen into the person in front of you.
It just went whee all the way around, and I ended up tail first in a snowbank.
One winter culprit is called black ice, but it's not what people think.
I imagine it's just ice mixed with oil, and that makes it that much more slippery.
Black ice is actually just ice, but it isn't more slippery, and it's not black at all. Rather, it's so thin and transparent that the dark color of the pavement shows through.
In many cases, when you drive down the roadway and there's black ice on the road will look just as it did on a dry day. You won't see very much of a difference. So black ice is somewhat transparent, and it's very difficult to detect.
Keeping cars under control depends on friction, the resistance to motion when two objects rub together. There's very little friction when snow and ice cover the roadway. With no friction, hitting standard brakes just locks up the wheels and cars skid and slide. Maintaining control is the goal of anti-lock brake systems, or ABS. The system is a series of wheel sensors, hydraulic and electronic controls that hold the brakes near lockup while keeping the wheels rolling to help the driver steer. In a panic stop situation, standing on the brakes without ABS sends this car into a violent spin. But with ABS, it's like the system automatically pumps your brakes. The tires never break traction, allowing the driver to control the car coming to a stop. It's always best to slow down in slippery winter conditions. But if your car does start to slide, experts say to look and steer in the direction you want to go. Keeping roads clear of snow and ice makes staying in control a cinch. That's one reason why big cities devote big bucks to snow removal. In a typical winter, about 28 inches will fall on the Big Apple. New York spends $35 million to clear all that snow. That's $1.25 million per inch. In Chicago, winter brings about 38 inches of snow. To keep streets passable, the city of Chicago deploys an army of 270 trucks. When hard hit with snow, the trucks will plow some 9,400 miles of city streets in a matter of days. That's equal to the distance between Chicago and Singapore. Snowplows have been around since about 1860. Even back then, a few cities tried using a chemical to fight snow and ice. But it fell out of favor because by melting the snow, it ruined the streets for sleighing. That chemical? Sodium chloride, more commonly known as table salt. Nowadays, road crews spread about 15 million tons of de-icing salt each year to combat ice nationwide. Why salt? Salt has the ability to lower the freezing point of water. So if it's 32 degrees Fahrenheit, with a sprinkle of salt, water won't freeze until the temperature drops to near 15 degrees. Thus keeping roads ice-free at temperatures below freezing.
It's basically the same salt that we use to season our food. It's sodium chloride, although in terms of applying it to the road, we're going to use larger grains.
But it doesn't have to be salt. Anything that dissolves in water will lower the freezing point. It would be sweet to sprinkle sugar on icy roads, but salt is less expensive.
490, yes, our approach is Alice, 23 left.
Ice on an airplane can also be deadly. In 1994, ice on the wings caused a commuter flight to crash near Chicago in Roselawn, Indiana, killing 68 people. Since then, more than 130 other people have died in icing-related crashes nationwide. Federal investigators have called for tougher rules and more research on flying in icy conditions. A surprisingly thin coating of ice will cripple a wing's efficiency.
For the case of icing when the plane's on the ground, as little as 0.08 of a millimeter can cause 25% decrease in the lift ability of the wing.
To get rid of that ice, ground crews use a common solution you'll find in your garage, antifreeze.
You hose off the ice with a heated solution of glycol and water, either propylene or ethylene glycol. And that's the stuff that you put in your radiator in your car.
But once in flight, de-icing is primarily mechanical on smaller aircraft.
It's very clever, actually. On the leading edge of the wing, often if you look at an airplane, you'll see this black surface there. It's rubber. It's filled with air channels.
When ice builds up on the leading edge of the wing, the channels are inflated with air, like a bicycle pump blowing up a tire.
It expands that surface and the ice cracks off, and since the airplane's going very fast, it just blows it away.
Altitudes up to 20,000 feet are known as the icing danger zone. That's where icing is most likely to occur. But don't look for the pneumatic rubber boot on big jet aircraft. They cruise in drier air above 30,000 feet, where icing is less likely. Here's one vehicle built just to drive on ice. Since it was first patented in 1953, people have been fascinated by this ice machine with a funny name. Its creator is an American inventor of Italian descent who just happened to own an ice rink, Frank J. Zamboni. As it glides around the rink, a blade hidden underneath the Zamboni resurfacer shaves the ice clean before putting down a layer of warm water, which smooths the surface before it freezes.
The forecast, cloudy skies with flurries today.
On a cold winter morning, a deep layer of fresh snow can be every kid's dream come true. A snow day, when school is canceled. Snow days make time for sledding, skiing, and skating fun. But none of that would be possible without the science of ice. There's no question that ice is slippery stuff. But did you ever stop and wonder why?
Ice is slippery because... Oh God, I really have no idea.
Why is ice slippery? Jeez. I think ice is slippery because it's made of water.
Conventional wisdom was that friction or the pressure of an ice skater's blade, for example, melted the ice, creating a lubricating layer of water. But friction doesn't explain why ice is slippery when you stand still. And in reality, skates do not create enough pressure to instantly liquefy the ice. A chemist at the University of California at Berkeley, Gabor Samorjai, discovered that ice is covered by a slippery quasi-fluid layer. In liquid water, the molecules move freely in all directions. Once frozen, the water molecules inside ice are bonded together more rigidly. But imagine a water molecule on the surface of the ice. It has no molecules to bond with above it. So these molecules are free to vibrate up and down. That's how they imitate a liquid and stay slick and slippery. Sliding on ice is how downhill skiers make tracks in winter. Snow is, after all, made of ice crystals. It may surprise you to know that skiing has been around for 4,000 or 5,000 years. The oldest known ski found preserved in a bog in Huting, Sweden, dates to 2500 BC. The earliest skis, presumably, were made from bones of large animals and were strapped to shoes with leather thongs. The father of modern skiing was a Norwegian potato farmer named Sondre Norheim. In the 1860s, Norheim popularized a turn that allowed skiers to traverse steep slopes. A skier who heads straight down a 30-degree slope can reach 150 miles per hour, but making turns back and forth across the hill keeps speed under control. The sport taken to its extreme sends skiers flying. In the freestyle aerials event, skiers hit a ramp called a kicker at about 45 miles per hour, launching themselves into gymnastic somersaults, turns, and twists. In winter, they will land on a steep snow-covered slope. In summer practice, the landing zone is a pool. The splashdown softened by a huge injection of air.
The most important part of the jump is landing. There's a lot of force when you hit the water. It's actually a harder force than when you hit the snow. We have a bubbling system under the pool, and it aerates the water, so it makes it less dense, so they sink into it a little easier and reduces the impact.
Winter athletes in the luge event slide just inches above an icy track. The riders call themselves sliders. They train to put as much muscle as possible into the start.
1, 2.
Once they're underway, the force of gravity is their motor. Friction and aerodynamic drag are brakes.
You're not thinking so much of the speed, but how can I go faster?
Hitting speeds above 90 miles per hour, sliders fight high G's in the turns.
It's kind of like a fighter pilot. When he's pulling G's, when he's making his turns, we'll peel 4 to 5 G's in the curves, 4 to 5 times my body weight.
Sliders may have the nerves of a fighter pilot, but the toes of a ballerina.
Rapidly pick up speed through here.
We're always in an aerodynamic position with our toes pointed straight ahead so that we punch a nice clean hole through the air and the air flows around us. If your feet are flat, you're blocking a lot of air with your feet, and that's going to slow you down.
The speed and the G-forces can get the best of them.
It does happen that you can't physically hold your head up through some of these curves, and it pulls your head all the way back to the ice, and you're now looking where you've been and not where you're going. It's really not a pleasant feeling to not be able to see and have your head bouncing along the ice behind you.
And when that happens, the ice wins. In the U.S., nearly 7 million skiers hit the slopes every year. Each one of them wishes for that dreamlike run through deep, fluffy powder snow, because it feels like you're floating through a cloud of snow.
If you ask skiers what's the best kind of snow, it's the very loose powder is always made of this one kind of snow crystal, which are called stellar dendrites. They're very thin, star-shaped with very large branches and side branches. And because they're so large, they kind of interlock. They don't pack very densely.
So it's the shape of the stellar dendrites that make the loosely packed fluffy powder. But when nature doesn't deliver, snow-making machines take over. Snow guns inject water into a flow of compressed air, breaking the water into a mist of small particles. As the compressed air expands, leaving the gun, it cools in a flash.
And it cools so rapidly that the droplets freeze. And then a fan just pushes them out onto the slope.
And it takes a lot of water. Making 6 inches of snow on a 200 by 200 foot slope uses 82,000 gallons of water. That's 11 tanker trucks full. But nature will never be outdone by artificial snow. Artificial snow doesn't pile up like powder. It packs tightly because of its shape.
If you look at those crystals, and I've taken pictures of them, they're actually little round globs, what you'd expect from little frozen droplets. Not at all like the really nice snowflakes.
Olympic ski jumpers hit 60 miles per hour and fly through the air the distance of more than 2 football fields. But to get that good, they have to practice all year round, even in the heat of summer. So when the temperature soars, a porcelain track stands in for ice. And plastic mats sprayed with water make for slippery, soft landings. As much as humans are unequipped for winter, some animals are perfectly suited for nature's coolest season. Arctic winter weather poses no problem for the great white polar bear. Their secret? Insulation. Polar bears have 2 to 4 inches of dense fat to keep them warm. Polar bears are so well insulated from the cold, they are invisible to heat-detecting infrared cameras. And that's just one of their winter survival systems.
If you sheared off the fur of a polar bear, you would find their body is pure black. And so that works in their favor because when the sun comes through their fur into their body, the black absorbs the heat. They can stay warm that way.
Additionally, much like the way humans trap air between layers of clothing to stay warm, the polar bear traps air in its fur.
And so that actually, almost like a mini greenhouse effect, traps warm air and keeps their whole body warm. So they're perfectly designed to live in the Arctic.
The polar bear's Arctic neighbor, the walrus, is a behemoth that's also perfectly outfitted to survive the coldest winters.
This 2,000-pound animal, about 15 feet long, has these 3-foot tusks, these dagger-like tools on the front of its face, and they're amazing animals.
Walruses react to the cold the same way a hypothermic human body does. When a human gets too cold, blood is squeezed out of the vessels in the extremities and pushed to the body's core. In a walrus, the same thing happens. Blood is steered to where they need it most, close to their internal organs, keeping their temperature near a toasty 98 degrees, even when swimming in bone-rattling 30-degree water.
Walruses will stay in the water for 8 days at a time. They'll actually shunt their blood just to the middle of their body, to their heart. And they just let a little bit of blood out to their flippers to keep them from freezing. And so when you see a walrus get out of the water that's been in it for 8 days, it's pure white. And then after it gets out of the water and it starts to warm up again, its whole body turns a pinky, kind of a red color.
The walrus changes from white to red because as they warm up, the blood flow returns to their skin. Walruses and polar bears stay active throughout winter. For some other animals, winter survival means taking a long nap. By dozing through winter, the bear is thought to reign as the king of hibernation. But bears are light sleepers compared to the real pros. At the University of Wisconsin, researchers simulate the dead of winter for a colony of squirrels.
You can actually see him shivering to generate heat.
Hiding in their nests, these sleepy little critters could hold the key to survival for thousands of people waiting for organ transplants. The 13-lined ground squirrel, named for the stripes on its back and sides, is able to slip into a kind of suspended animation called torpor.
That's the physiological term, torpor, for going into depressed metabolism and low body temperature.
So an animal in torpor has somehow slowed its metabolism. The term hibernation is used to describe the seasonal period when animals use torpor to save energy.
This is a female 13-lined ground squirrel who's in torpor. You can see her eyes are closed. She is breathing. It's at a very slow rate, but this would take a couple of hours for her to fully arouse out of this torpid state.
This squirrel's degree of metabolic depression is much greater than the supposed king of deep sleep, the bear. Both animals will hibernate for roughly 6 months. But while a bear's body temperature drops around 12 degrees, the squirrel's temperature plunges about 60 degrees and can hover just above freezing.
Since he started hibernating.
The squirrel's breathing and heartbeat slows, its kidneys shut down completely.
Lots of body fat still remaining.
What interests Dr. Carey is that during torpor, the squirrels chill to the same temperature used to store human organs for transplant.
When organs are harvested from a donor, they are typically cold stored prior to transplant into a recipient. The longer an organ is cold stored, the more damage accrues, and the worse that that organ will do after it's transplanted.
But after months of hibernation, the squirrels arouse with no damage to their organs. Some unknown mechanism, perhaps a protein in the blood or a gene that regulates metabolism, prepares the squirrel for torpor and protects its organs.
So our studies are aimed at trying to understand exactly how that happens and use that information to improve cold storage conditions for organs that might be transplanted.
Finding the secret to the torpor phenomenon could make organs more readily available to patients whose lives depend on them. While Dr. Carey studies the 13-line ground squirrel, across campus, Dan Young is focused on much smaller creatures and how they manage to survive winter.
I don't know if it's a myth, but one of the things that people commonly think about winter is that insects are somehow all gone. Summer means insect activity, and in the winter, everything dies.
Wow, where do the bugs go in the winter? Well, the bugs go? I think they get frozen to death in the winter.
I think the bugs die in the winter because it's so cold, especially mosquitoes.
People say, well, good, we had our first hard freeze, the mosquitoes are all dead. Well, mosquitoes aren't all dead, they're just in a different stage. Many of the adults have died, but what typically is going to happen is that the egg stages are going to make it through the winter.
Even in the harsh Alaskan winters, most types of mosquitoes survive as eggs submerged under ice and lie dormant until spring. As temperatures rise, the eggs hatch. These mosquitoes and some other insects prepare their bodies much the same way we protect our cars.
Just as many of us are heading over to the repair shop to get the antifreeze level checked on the car, a lot of insects are doing that too. And in fact, some of the compounds that they produce are very much like the antifreeze. It's chemically very similar. Glycerol is a compound that many insects produce that prepares them for winter.
Being prepared is the key to the insect's survival. Humans prepare with a good weather forecast. Legend has it that on February 2nd, a hibernating groundhog in Punxsutawney, Pennsylvania, can predict if there will be 6 more weeks of winter. But the story that this rodent will come out of its burrow to check the weather is just that, a story.
No groundhog worth its salt would come up in the middle of winter and take a look around. They're happily living off of their body fat in their nice nests down underground in the burrows, and really don't have much reason to come up and look around.
Winter will come to an end right around March 20th for those of us in the Northern Hemisphere. But as you await the arrival of spring, keep in mind that every snowflake, slip, skid, and shiver is the result of the science of winter.